All right, so now we are going to do our last lecture video dealing with equilibrium. And it's just a very important principle that goes along with the topic of equilibrium. And this principle is named after a French guy who derived it, Le Chatelier. It's my best worst French accent. I don't know what that little caret does over the A, but it's named after him. So this principle states that if a stressor or a disturbance is applied to a reaction that is at equilibrium, then the reaction will proceed in the direction that's required to re-achieve equilibrium. Okay? So the really important part about Le Chatelier's principle are these stressors or disturbances, as sometimes they're called. And these disturbances or stressors act to kick the reaction out of equilibrium. Okay, let's say we already have a reaction that has achieved equilibrium, but then we do something to it to throw it out of whack. It's not in equilibrium anymore, but it wants to get back to equilibrium. So this principle tells us how that reaction will get back to equilibrium. Okay? Now, you might be asking, maybe, I don't know, one or two of you might be asking, well, why does a reaction need to be at equilibrium? Who cares if a reaction is at equilibrium? And the answer to that, hopefully, you might already know, because a lot of times whenever you kids ask, well, why does this happen? Why does that happen? Why does this happen? There's usually a pretty generic answer that kind of applies to a lot of different phenomena. And maybe if you're in my class, maybe you'll remember. Good, it's because it's energetically favorable for a reaction to be at equilibrium, right? So these reactions are most stable, the lowest amount of energy, when they are at equilibrium. So naturally, reactions will go towards equilibrium so that they get that lower amount of energy, okay? So what we're going to concentrate on now are these stressors or these disturbances that you can use to throw a reaction out of equilibrium and then watch how that reaction responds to get back to equilibrium, okay? Now what I'm going to do is use the generic reaction that we were using in the last video. Hopefully you guys are familiar enough with that I can use it for these examples. So it's 3A, that's aqueous, plus 2B, that's a gas, is in equilibrium with C, that is a solid, plus 2D, that is aqueous. Okay, so this was our generic equation that we first wrote the KEQ equation for back in the last video. And what we're going to do first is maybe the easiest disturbance or stressor that you can do to a reaction to throw it out of equilibrium, and that is to either add or remove substances from the reaction. Now, why would adding or removing a substance throw a reaction out of equilibrium? Hopefully you realize now that quantitatively we define our equilibrium of a reaction as the concentration of products over reactants. Well, if you change the concentration of a product or a reactant by adding or removing it, you're obviously going to throw it out of equilibrium, okay? So this is the easiest one. Maybe you guys were thinking about that as a disturbance because that would be a very simple way to throw a reaction out of equilibrium, okay? So let's think about what would happen if you add a substance. So let's say we add extra A to our reaction. Now remember, we're already at equilibrium, and then we add A. So again, KEQ, just remember, I'll put it up here. KEQ is products over reactants. Get that in your head forever. Products over reactants. So if we add A, that's our reactant, we're going to increase the denominator, right? So it's going to throw it out of equilibrium. But the question is, which way would this reaction then proceed to gain equilibrium again? And so if we add A and we already have too much A, which way will this reaction have to proceed in order to get rid of some A? Hopefully you see it would have to go away from that addition, right? We're going to try to get rid of some A, so we're going to go from A towards the products to get rid of that addition. So if we added A, it would shift to the right, okay? What if we, let's say we remove some of the product D, okay? Let's say we remove some of this aqueous product. Well, now we have removed a product. Our numerator in our KEQ is lower. It's going to throw it out of equilibrium, but how do we get it back up? Well, we can try to create more of that product, and we can shift the reaction towards producing D, or again, shifting it right. So hopefully through these couple examples, you can see a general rule forming here, where if we add a substance, then we will shift away from the addition. Okay, we're going to have to shift the reaction in the direction that goes away from wherever you added substance to that reaction. Okay, in our example, we added A, so it's going to shift away from that towards the other side. Okay? Likewise, if you remove substance, just like we removed some of the product D here, we would have to create more of that substance in order to get back to equilibrium. So in this case, we will shift towards the removal, not addition, the removal. Okay, so shift towards removal if we remove, shift away from addition if we add. Okay, now what if I added or removed C in this reaction? C is a solid. Solids and liquids, remember, do not affect equilibrium. So you could remove C and it still will not affect the equilibrium state, okay? So the solids and liquids do not adhere to this rule because they don't play a role in our equilibrium constant. This chemistry lecture brought to you by Dogs Catching Treats. Sit. Good job. Oh! Okay, so we are going to do the last two stressors now, and these are the trickier ones. They're a little trickier than the last one, so bear with me. So the next one is if we change the pressure at which we are completing a reaction. So maybe you can think of a way that you can easily change the pressure of your reaction vessel. We learned about it in the gases unit with Boyle's law, which states that if the volume is decreased, then the pressure is increased, right? Because they're inversely related. So if you would just stuff your reaction in a 1 liter vessel compared to doing it in a 3 liter vessel, so you're decreasing the volume, that could increase the pressure. Likewise, you could do the opposite to decrease the pressure, okay? So there are many ways that you can actually change the pressure of your reaction that's occurring, but we're going to see if we use pressure as a disturbance, then how does our reaction shift to get back to equilibrium, okay? And so it's kind of simple what happens. So if we increase the pressure, and again, that could be done by squeezing this into a smaller volume, a smaller space. But if we increase the pressure, what this reaction is going to do is it's going to shift away from producing gas, right? Because that's what is causing the pressure from the system, is all of the gas that's created. So if you increase the pressure at which you're completing this reaction, the reaction itself is going to shift away from producing gas. Okay, so it's going to kind of counteract that additional pressure by trying to get rid of gas. Okay, so what you want to do to see which side is going to be favored or which way you're going to shift is you have to look at the substances that are in the reaction and their states as well as their coefficients, okay? Because if we increase the pressure, what your reaction is going to do is shift towards the side that produces less moles of gas, okay? So to determine which side has more moles of gas, just look at everything that's a gas. Here on the left, we have 2 moles of gas. On the right, we have 0 moles of gas. So if we increase the pressure, it's going to shift away from producing gas, so away from this gaseous reactant, and towards the side with less gas. All right, so increase in pressure, it's going to shift towards less moles of gas. And it's only gas that's affecting this equilibrium at this point, okay? Because we're just talking about pressure. The gas is the only thing that's accounting for pressure in your reaction. So it's going to shift towards less moles of gas if we increase the pressure. However, if we decrease the pressure, hopefully you can tell what's going to happen. We are going to shift towards more moles of gas. Okay, just like before, moles of gas, but now it's going towards the more moles of gas. It's going to try to counteract that decrease in pressure by increasing the amount of gas produced to try to get that pressure back up to the equilibrium state. Okay, so that's the second one. So this one is quite simple because we only have gas on one side of the arrow, but you could do this if you had gases on both sides. You would just compare the coefficients. Whichever had a higher amount of gas would be the more moles. Whichever had the smaller amount is the less moles. Okay, so that's the second one, change in pressure. And then our last one, is change temperature. Okay, and to think about this one, you're going to have to kind of think back to our last unit we did before spring break about energy. Because what you want to do is you want to think about the amount of energy that's either released or absorbed over the course of the reaction as either a reactant or a product. Okay, and we did this last unit, so maybe you'll remember. If a reaction, let's say, is endothermic, that means that the reaction has to absorb energy, and then we think about it as a reactant, right? We could just put heat on the left side of the equation if it's endothermic. If it's exothermic, this reaction is releasing heat, so it's acting more as a product. So we could add it as a product. Do it in a different color. So I am going to designate this made-up equation, this made-up chemical reaction as exothermic because I wrote it as a product, okay? So if we increase the temperature, basically you can think of that as adding heat, right? You're adding energy if you increase the temperature of the system. So if we increase the temperature, we are basically adding a product in this case. Then it just goes back to the first disturbance of adding or removing a substance. You can just think of heat as a substance like A, B, C, or D. So if you increase the temperature, you're going to shift this reaction away from the heat. Okay, so it's going to shift away from heat. In this case, it would shift towards the left because it's exothermic and heat is a product. However, if you decrease the temperature, hopefully you can deduce what's going to happen. We are going to instead shift towards the heat. Okay? Now, the hardest part really is just making sure you put heat on the correct side of the arrow, right? Make sure if it's endothermic, you're going to put heat as a reactant. If it's exothermic, it's going to be a product. Then it's just shifting it either away or towards that substance that you just added to your reaction. All right, good luck on your assignment.